Yeah.
Okay, so welcome everybody to this new IFIMAC plus ICMM seminar. It is a special pleasure for me to introduce today's speaker. Today we have with us Miguel Ugeda. Miguel did his PhD here at the Universidad Autónoma de Madrid in the Condensed Matter Physics department. During his PhD, he he first designed and built a scanning tunnel microscope operating in ultra-high vacuum and low temperatures. And then with this machine, he was able to investigate the properties of 2D materials, in particular graphene, and which was the influence of point defects in the electronic and magnetic properties of this material. Then he moved to UC Berkeley, to Mike's Chromic Group to do as a postdoctoral fellow, and there he continued with the research on 2D materials with STM, and in particular he moved to transition metal dechalcogenides. He stayed there for 4 years and got very good results, very successful postdoc he did, and then he got a Iker Basque fellow and also a Ramon y Cajal fellow, with which he moved to San Sebastian, to Nanogune, to the group of Nacho Pascual. There he started to investigate the properties of 2D materials, but now taking a look to its superconducting properties. And in a couple of years, he got an starting ERC grant, and he also became Iker Basque researcher, which means a permanent position, with which he moved to the Donostia International Physics Center, where he now leads his own group, and he continued working with his main experimental technique, which is scanning tunneling microscopy and with 2D materials. And I think today he will show us some exciting results that he's doing in his new group. And now, before giving the word to Miguel, I would just like to remind you that during the talk, microphones will be off, so no questions can be done, but just when Miguel finishes his 45 minutes talk, more or less, you will be able to unmute your microphones, also to switch on the video, and then you can raise your hand with Zoom, and then you will be allowed to make questions, and we can hopefully have a fruitful discussion. So Miguel, the audience is all yours. I'm looking forward to see your exciting new results.
Okay, so can you hear me? Good afternoon, everyone. So first of all, let me thank Ivan, Isabel, and the rest of the organizers for inviting me to participate here today and giving me the opportunity to share some of our latest results in this group. As I said, as Ivan said, I belong to the Donostia International Physics Center, but also to the Centro de Física Materiales, where we actually have the labs. And as you can see today, I would like to talk to you about something called unconventional superconductivity in two-dimensional van der Waals materials. In particular, I will focus on transition metal dechalcogenides. However, before I get started, please give me some minutes to acknowledge and thank the people involved in the results that I will show you today, but in general to the project of two-dimensional superconductivity. So of course, I would like to start with my own group. Wen Wang, who is a postdoc here, Paul Dreher is a PhD student. These two folks have done most of the work that I will show you today. Rishabh is a postdoc who joined the group like 1 year ago. He's getting involved as well in this project. We have had the theoretical support, or we constantly have the theoretical support by Paco Guinea and Fernando de Juan at the DIPC and INDEA. And also, I'd like to thank Felix Indurain because he's doing beautiful DFT calculations on these superconducting systems. So our colleagues at the Universidad Autónoma de Madrid, in particular the group of Antonio Martinez Galera, is doing, I will show you some, they are doing particular substrates to decouple our 2D superconductors from the rest of the substrate. I will show you some preliminary results about it. our colleagues at the Aarhus University. They are carrying out beautiful ARPAS results on these systems. And finally, I would like to thank Santi and Marco Gobi from local researchers here, taking care of the magnetic measurements on these systems, and as well the device. They're pushing the implementation of these materials into devices. Okay, having said this, as I said at the beginning of the talk, today I would like to talk to you about unconventional superconductivity. And since Ivan told me that I should give a didactic talk, let me spend some minutes explain what we mean by unconventional superconductivity. So, okay, I guess most of you are totally familiar with the phonon-mediated Cooper pair formation mechanism, which is somehow illustrated here. Now, basically, one electron passes through a particular region in space, and the ion lattice gets distorted. So, in other words, this electron emits a phonon to the lattice, and basically this region becomes positively charged afterwards. And this region is it's an attractive region, it becomes an attractive region for a second electron that eventually absorbs this phonon. So this is the phonon mediated of this exchange of phonon is the way, the conventional way to explain the formation of Cooper pairs in superconductors. But you should note that this is not the only one, the only mechanisms possible. And that's what we refer by unconventional superconductivity in general, right? So any mechanism for the Cooper pair formation that it's not driven by phonons. For example, it's well known now that despite the repulsive Coulomb interaction, the effective electron-electron interaction can become attractive for electrons in space and time regions being mediated by a spin or charge. So in this case, the glue, the pairing glue could be the spin or the charge. In particular, it's quite important that the role of a spin, because many different unconventional superconductors are believed to be mediated by a spin-spin interactions. Okay, so the phonon-mediated superconductivity, it's well explained by the BCS theory, which was developed in the late 50s, and usually, and it leads to superconducting order parameters that are isotropic in the momentum space, as you see here, and the Cooper pair is formed by singlets, so spin up, spin down Cooper electrons. In the case of unconventional superconductivity, generally the symmetry of the superconducting order parameter is lower, as you see here, for example, in this example, and the Cooper pair can be formed by either singlets or triplet pairs of electrons. This is what we usually refer, the most generic definition of unconventional superconductivity refers in general to non-phononic mechanisms for the phonon dispersion. So here in this plot, I show you the critical temperature of several superconductors as a function of the year where we discovered. And as you can see here, from the very beginning of the era of superconductivity in 1911, and for 70 years after its discovery, you can see that most of the, or all of the superconductors that were found are conventional superconductors, and actually they all, the superconducting properties were well explained by the BCS theory, which was developed in 1958. So at this point of at the end of the 70s, what believed that most or all the superconductivity was a nailed problem, but just in 1979, it was discovered this material as a superconductor is this cerium copper silicon based material. And it was clear that the superconducting properties of this material didn't fit the BCS theory. And shortly after the discovery of this material, others came, these uranium-based materials, which also didn't fit the BCS conventional theory. So it's interesting to see that it took 70 years to discover these materials, because after that, now we know that there are many different families of unconventional superconductors. For example, you can see the remarkable example of cuprates with very high critical temperatures, or the more or the most or the family of iron-based superconductors, which were discovered in 2008. So as you can imagine, the superconducting properties of all these families of superconductors is quite diverse, quite different. And however, there are certain common characteristics of all or most of these unconventional superconductors. One of them is that in general, unconventional superconductivity in these materials is generally sustained by D or F electron cations. So there's one remarkable exception, which is the twisted bilayer graphene, as you all know. But in general, the D electron, F electrons basically drive the superconductivity in these materials. These are electrons which in general are subject to a strong electron-electron correlations, and in general lead to many body phases. Another common characteristic of these materials is that in general they have a strong structural anisotropy, a strong two-dimensional character. Here I show you an example where you can see this cuprate, where the superconductivity is basically confined within these yellow planes, and it's surrounded by insulating planes. So the superconductivity is somehow decoupled between the superconducting planes. And finally, another common characteristic of these unconventional superconductors is that generally superconductivity is usually developed near ferromagnetic magnetic phases. In general, they usually develop around something called quantum critical points. Here at the onset of a phase transition, a magnetically ordered phase is a second order phase transition. So it's the perfect place for superconductivities to develop in a region where the magnetic fluctuations are significant. Here I show you a couple of examples of these two heavy fermion compounds. In this particular one, superconductivity is developing near the antiferromagnetic dome. And for this uranium-based heavy fermion compound, the superconducting dome is actually not overlapping, but inside the ferromagnetic phase. So they are both phenomena are coexisting actually. Okay, so there is a long list of typical fingerprints that can be, or that rebuild unconventional superconductivity in these materials. Here I list some of them. Let me highlight some of them. For example, they usually show the existence of pseudogaps above the critical temperature. They in general present spin resonances below the critical temperature, and this is something that I will focus on today. Or for example, it's well known that unconventional superconductivity in general is quite sensitive to non-magnetic disorder in contrast to the conventional superconductors. So it doesn't mean that every unconventional superconductor have to fulfill all this list of phenomena. Could be that it only fulfills one of them, but this is something that in general, give warnings about the unconventional character of superconductivity. So despite of this list of typical fingerprints of unconventional superconductivity, there is no yet an unified theory about unconventional superconductivity. It's not even known that if there should be one that basically takes all of the unconventional superconductors within one single theory. So it's quite hard to study unconventional superconductivity, and one of the reasons, that's my personal opinion, is that that there is a high complexity associated to the study of bulk unconventional superconductors, and one of the reasons is because these materials in general show a very complex phase diagram. I show you here one of the examples. So the superconductivity is constantly surrounded by many body phases, and it's this phase diagram is highly dependent of the exact amount, for example, of doping in the case of cuprates, for example, or pressure, strain, etc., etc. And that makes quite challenging to study these materials for both for the theoretical point of view, but also from the experimental point of view. The other reason is that in general, the stoichiometry of these unconventional superconductors is could be quite complex. As you see here, I show you the unit cell of these cuprates, where you can see that many different atoms and planes are involved in the unit cell. And that, of course, makes also very challenging to model these kind of systems in order to learn about unconventional superconductivity. But also, it makes it quite challenging for experimentalists where they try to grow these materials or characterize them after the growth, and usually lead to quite different results. So one alternative to these bulky unconventional superconductors would be two-dimensional superconductors, but here we have faced a problem historically. So here you have the evolution of what's been called two-dimensional superconductors. Back in the 80s and the 90s, the best approximation to two-dimensional superconductors were, in general, disordered thin layers of elemental materials like bismuth, palladium, or even other materials, but with a very easy stoichiometry. But the things changed like 20 years ago or so with the emergence of new two-dimensional superconductors. Here I show you some of them. So it was able to grow crystalline layers of lead, indium on a particular substrate, or, for example, to grow monolayers of iron selenide on STO. Also, it was discovered some interfaces which resulted superconductors, or even MOSE2, monolayers of MOSE2. The problem with all these superconductors, though, is that they are not intrinsic superconductors. So it means that they only show superconductivity because they are grown on a particular substrate, or they are on a device, etc., etc. And that's a problem, because we want intrinsic superconductors regardless of where the material is. And only 5 years ago, this field of intrinsic superconductors exploded finally. Here I show you some of the most remarkable intrinsic 2D superconductors, niobium diselenide, of course, in the monolayer or in the thin film regime. These materials are highly crystalline and can be studied in many different substrates, and they retain the superconducting properties. Remarkable example is, of course, the twisted bilayer graphene or monolayers of these cuprates. However, and despite the progress on the development of the field of 2D superconductors, the Cooper pairing glue in these materials has been barely explored. It's a 5-year-old field, so nobody knows exactly what is driving superconductivity in these materials. It seems clear that it's probably not conventional superconductivity in all the cases, but it's far from being understood. So as you have seen in the previous plot, most of these two-dimensional materials are TMD materials, transition metal dichalcogenides. These materials have been studied in bulk for many years, actually decades. The atomic structure of these materials is quite simple. It's basically formed by an atom of a transition metal element sandwiched by 2 layers of chalcogen atoms in this or similar unit cell. And in 3 dimensions, so superconductivity is already developed in these materials. For example, you have the case of niobium diselenide that has a superconducting critical temperature of 7 Kelvin, or the case of tantalum disulfide with a critical temperature of 0.7 Kelvin. In 2 dimensions, however, this field is still to be explored mostly. It's known now that niobium diselenide in the single layer form has a critical temperature of 2 Kelvin. Or, for example, a single layer of tantalum disulfide has a critical temperature of 3 Kelvin, but there are other materials that has not been studied. And of course, what mediates superconductivity is not known at all. But if you look carefully at the properties of these materials, it seems clear that they are in a good position to satisfy or fulfill their common characteristics of bulk unconventional superconductors. I will go through all of this in a second. And there is one more important thing about these 2D superconductors, which is that in the single layer limit, they lack of inversion symmetry the lack of inversion symmetry. I'm not going to get into details about this, but it's known that a two-dimensional superconductor where there is a lifted spin degeneracy, for example, due to spin-orbit coupling. Spin-orbit coupling is something quite, spin-orbit coupling is something quite significant in these materials in the two-dimensional limit. Then in this condition, a mixed singlet triplet state should develop. Okay, so that's something to take into account as well in order to study these materials. So let me go back to the common properties of TMD materials. So, well, yes, unconventional. This superconductivity is sustained as well in these materials by d electrons in this case, depending on the material that you are talking about. For example, niobium diselenide are 4D electrons. These electrons in general have demonstrated in these materials that lead to quite strong electron correlations, and actually it has been experimentally detected many body electronic phases, such as mode phases, magnetic order, or even quantum spin liquids in these materials in the single layer form. It's also known that two-dimensional TMD materials, and due to the reduced screen charge carrier screen in this material, when you reduce this material into 2 dimensions, the reduced screening leads to enhanced electronic interactions, which accentuate somehow these electronic correlations and promote even more these many body phases that I was talking about in a minute. But there's another consequence of this, is that all of these many body phases in general have a tendency to diminish the density of states at the Fermi level, which is not beneficial at all for conventional superconductivity. And finally, so these materials seem to be also close to the magnetic state. We know this nowadays because of 2 works. The work by Professor Felix Indurain at the Universidad Autónoma de Madrid. He studied in collaboration with Daniel Sanchez Portal here at the CFM using 2 different codes, Siesta and BASP, the ground state for bulk niobium diselenide and monolayer niobium diselenide. And it turns out that no matter the code that they use, no matter the pseudo potential that they use, the monolayer seems to have a ferrimagnetic ground state, as you see here. This is the LDA approximation, including van der Waals, etc., etc. No matter what they do, the ground state is always ferrimagnetic in the form that you see here. Okay, so apart from this work, there has been other work by the Professor Massin claiming something quite similar. In their case, they don't claim that the niobium diselenide is a ferromagnetic, but they demonstrate theoretically that niobium diselenide is close to a ferromagnetic instability, and they actually discuss the possibility or the impact of this ferromagnetic instability in niobium diselenide on superconductivity. And they claim that it's pronounced in monolayer and in principle can enable seizable singlet and triplet mixing in the superconducting order parameter. That's a theoretical work, and that's all we know. So let me go back for a second to the idea of having superconductivity without phonon. So how can this be possible? So here I show you, a sea of quasiparticles interacting, sea of quasiparticle interacting. So what is the effective potential that this particular quasiparticle fields? So the expression is this one. It has two terms. One is proportional. This first term is proportional to the density or charge density of the system. And the second term is proportional to the magnetization that this quasi-particle feels at this particular position. If we now simplify the problem and just consider two of these quasi-particles, we can substitute the magnetization, but by the spin of this probe quasi-particle, and basically the magnetization becomes simpler with the non-local magnetic susceptibility times the spin and times the strength of the coupling. Okay, so we put this magnetization into the effective potential. Basically, we still have two terms. One of them is, accounts for the charge density, and the second one, which is particularly important, depends on the particular spin-spin interactions mediated also by the non-local magnetic susceptibility. So it turns out that if you tackle this problem using quantum electrodynamics, of course, this is a very complex problem to solve. But if you tackle this problem, basically you realize that, or you can learn that at the border of either ferromagnetism or the border of antiferromagnetism, this term can be quite relevant because the magnetic susceptibility, it's prone at the border of ferromagnetism. So basically, for example, in the vicinity of ferromagnetism, spin triplet configurations are favored, okay? And given the sign of this material, can be demonstrated that the magnetic susceptibility is maximum at the origin and decays monotonically with the distance, yielding an attractive interaction in this second term. So this is the effective potential interaction that this spin triplet configuration fills. In the case of in the border of antiferromagnetism, the situation is a bit different, and then singlet configurations are favored, and given the sign of this inner product, basically you have to look at what happens at the magnetic susceptibility. In this case, the magnetic susceptibility and the presence of antiferromagnetism is also maximum, but it does not decay. Monotonically, but it fluctuates. The sign of the magnetic susceptibility fluctuates in sign, and so does the induced effective potential between these two quasi-particles. So that's why, in principle, spin-spin interactions can mediate superconductivity without the need of phonons. Okay, so today I will focus on single-layer niobium diselenide and not on tantalum diselenide. I know that in the abstract I also talked about tantalum diselenide, but we are still studying it, and we believe that it's a bit more complex than the case of niobium diselenide, so I don't want to mess it with it. So we'll focus on niobium diselenide, which has a simple band structure in the single-layer limit. It's basically, this is the only band that crosses the Fermi level, the only band that matters in terms of the superconductivity. As you see here, this band splits at particular regions in the brilliant zone, in particular here close to the K point, okay, due to the presence of the spin-orbit coupling. So these are the subband, spin-up subband, and the spin-down subband. But other than that, the electronic structure is quite simple. So we know from previous measurements that single-layer form of niobium diselenide retains the challenge-to wave that was observed for bulk in a similar 3x3 configuration. So what you see here, apart from the atomic registry, is the 3x3 supermodulation that comes from the challenge-to wave. And we believe that the critical temperature is quite similar with respect to that found in bulk, which is 30 Kelvin. In terms of superconductivity, this material in bulk is a superconductor. It has a critical temperature of 7 Kelvin, and it's a multiband superconductor. So you can see in the DIDV spectra that there are two different gaps. One of them is 0.7 millielectron volts, and the other one is 1.4 millielectron volts. When you go to the single-layer limit, the system is still superconducting, but around with a critical temperature of around 2 Kelvin. Okay. This is the experimental setup where we have carried out most of our experiments. This is the MBE, the UHB MBE instrument working in ultra-high vacuum conditions. Here you see when growing one of the samples. So after the growth, basically what we do is to cap the 2D material with a amorphous selenium capping layer that we allow us to transfer the material, the sample, to any other UHB system to further characterization for XPS, ARPANES, etc. And the main tool for us is this system. It's a UHB STM that works at a base temperature of 300 millikelvin, and we are allowed to apply a magnetic field of 11 Tesla. So once we get this sample into the prep chamber in this second system, we basically anneal at very low temperatures, around 200 Kelvin, and that's enough to remove the capping layer of selenium and expose the crystalline TND superconductor. So this is for those of you who are not familiar with the molecular beam epitaxy methods, just I will tell you that we can grow these materials. We have mostly grown these materials on bilayer graphene on silicon carbide for these experiments. We have also done it on single layers of HBN on a iridium 111 substrate that I will show you in a few minutes. But in general, basically, the MBE growth is based in UHB, and we grow it from the pure ultra-pure elemental materials. And in this case, we use pure niobium and pure selenium. And all we do is to keep our substrate heated, heat. We apply some heat to keep it at high temperatures while we perform the growth. We can track the evolution of the growth using read in situ. So here I show you that the diffraction patterns coming from graphene before the growth and the emergence of some additional lines or some additional diffraction pattern that comes from our TMD. So after this growth, and in order to optimize the recipe for niobium dicyanide and other TMD materials, what we usually do is to take these materials to the XPS or the AFM in order to control and optimize the morphology of the material. So here I show you an AFM, large-scale AFM image taken in ambient conditions of one of these samples of niobium dicyanide. Here I show you the large-scale morphology of one of these samples. These are tunnel microscopy images where you can see that basically we can either work with coverages as our will, but basically we usually work with coverages slightly below 1 monolayer because we're interested in having the graphene substrate as well as a reference. But in general, the typical size of our domains is like around 400-500 nanometers, as you see here. Here I show you another atomically resolved STM image where you can see the emergence of the 3x3 channel-city wave. But again, we can also complete the monolayer of niobium dicyanide if we needed to. So in terms of the electronic structure for niobium dicyanide, we demonstrated, or some of us demonstrated a few years ago, that the electronic structure becomes quite simple in the monolayer limit. Here I show you some large-scale ARPANES spectrum where you can see that the dispersion of the two pockets in these materials coming from, particularly you see this pocket here and this pocket here. The fact that you see it in the same spectrum is because so there is some sort of rotational disorder in the niobium dicyanide sample with respect to graphene, and that makes that we lose the angular resolution. But other than that, still we can distinguish these two pockets. And this is how, and here I show you a DADV spectrum taken on this single layer, where you can see that the critical, the density of states looks like this, and that's it. So if you go now to close to the Fermi level and at enough low temperatures, for example, I show you a DIDV curve taken at 2 Kelvin, so above the critical temperature for the superconductivity, but well below the critical temperature for the transit wave, you see that what we usually see is a gap. It's a gap and a finite a gap with a finite conductivity that we identify as the transit wave gap that has a width of 4 milli-electron volt, which fairly corresponds to the critical temperature that we found in this system. So if you lower down the temperature at 300 millikelvin, what you find instead, and you go even closer to the Fermi level, what you see instead is a clear development of a gap, where you see here, these are the, we know it's corresponds to the superconducting gap. These two are the coherence peaks. I don't know where the coherence peaks. And actually, in light blue, you can see the fit to the BCS conductivity density of states. And as you can see, the fit is it's very well up to the coherence peak. But when you go to the Bogoliubov quasiparticle region outside the gap, things start to be a bit more strange, because they don't decay monotonically, and what we normally see are these characteristic Dick Hamp features that are repeated more or less periodically outside the gap, and in general, not always, but in general, are symmetric with respect to the Fermi level. So these are non-VCS features that we have investigated further. So here I show you 4 examples taken with different tips, physical tips, not just tip apex, physical tips, on different samples on different days. Everything was different, and still we see very often, or almost always, these characteristic peaks. And as I said, they are in general quite symmetric with respect to the Fermi level, and there is some sort of symmetry, and they are quite equidistant between each other. It's not always like this. So in order to put some numbers and quantify the emergence of these satellite peaks, we have done some statistical analysis. We have taken thousands of curves taken in hundreds of different places. And this is the resulting statistical analysis that result in histogram for all of our curves, where you can see 5 different peaks. The first one corresponds to the coherence peak, corresponds to the existence of the coherence peak at a energy of 0.5 milli-electron volts. Keep in mind that even when I describe this as a superconducting gap, basically it's not the VCS gap, it's just the distance between the Fermi level and the position of the superconducting gap. Okay, that's why it's a bit larger than the VCS fit. Okay, but it's okay. So we have used this definition from in general. So apart from the coherence peaks gaps, there are another 4 peaks that you see in the statistical analysis in the histogram, and we can basically fit all these peaks and show that basically we find 4 different satellites at these energies: 0.5, 1, 1.6, and 2.2. So given the energies at which we find these satellite peaks, we basically attribute these 4 peaks to the existence of a fundamental mode omega-1 that we call here. And we believe that what we are seeing is a fundamental mode followed by some harmonics that I will show you in a second. So basically, they all follow this repetition rate, right? So what's the origin of these features? Okay, so one may argue that probably these features in the STS, in the density of states, may come from the boundary structure, but that's something that it's quite difficult to believe. So we don't believe that this is reflecting any feature in the boundary structure because, as I said before, and in particular within this energy range, there should be nothing in the boundary structure. So there are two pockets, and we don't expect any particular feature in the boundary structure. So another possibility could be the existence of multiple superconducting gaps in this system. But we have learned by the beautiful experiments carried out in Manchester a few years ago that the evolution of this multi-band superconductivity in iodine diselenide is general. So in this experiments, they didn't reach the monolayer, but in any case, for two layers, it seems quite clear that, it seems quite clear that the superconducting, the density of states in the two-dimensional limit only shows one superconducting gap. Okay, so we can probably rule out the existence of multiple superconducting gap. So what's left to consider are the existence of bosonic modes, which is something that it's quite common or in superconductor, not just in unconventional superconductor, but also in conventional superconductors. For example, we have chosen the three most common ones, which are phononic modes, spin resonances, or the Higgs modes. So the phononic modes is something that you can observe in conventional superconductors, and basically the glue in conventional superconductors are phonons. So what you see here is basically the interactions between the quasiparticles and the mediator, in this case, phonons. So this is an electron boson mode that you see here. In general, here you can see some shoulder deep humps in the density of states of lead 111. This is the superconducting gap, and in a symmetric way as well, you can see some features that are phononic modes. Something characteristic about these phononic modes is that, in general, the energy at which they are found is in general much larger than the superconducting gap. Here, actually, you see that they lie well beyond 2 delta. I will tell you why this is important, but the energy at which you find these two features is well larger than 2 delta. We don't believe these features that we see in single layer iodine diselenide can be phononic modes, and the reason is because there are, in general, if you see these features in a superconductor, there should be peaks in the density of states in the phononic dispersion. So if you calculate the phononic dispersion, and if you take into account the strength, the coupling strength with the electrons, basically what you see in lead 111 is that there are two. I don't see the mouse. You see basically two peaks, omega 1 and omega 2, that are somehow reflected here at the same energies. So the phonon dispersion of single layer iodine diselenide has been already calculated by Felix Indurain and Jon Herrera here as well, and they don't observe any particular or important feature in this small energy range, which is plus minus 3 milli-electron volts, where we see our features, our satellites. So another more serious candidate could be the existence of amplitude and Higgs modes in iodine diselenides. Basically, an amplitude or a Higgs mode is basically arising from the fluctuations of the order parameter amplitude here. So the amplitude of the superconducting order parameters can fluctuate, and that leads to the emergence of some collective mode in the density of states, or in principle visible into the density state. This is a dark mode, though, and that means that it's only visible when this mode is coupled to a different electronic phase, different from superconductivity. And that's the reason why, by the way, it's being observed in niobium diselenide, but in bulk. So the energies at which these modes are lie in the region where we see our satellites. So that means omega smaller than twice the superconducting gap, and actually they have been observed in bulk niobium diselenide using Raman spectroscopy at very low temperatures. So basically this mode, and the reason why it's been observed in niobium diselenide is because this Higgs mode is coupled to the Charles-City wave and becomes visible. The problem is that, so if you see here on the left, this is the density of states for bulk niobium diselenide, and basically the effect of this Higgs mode has no effect on the density of states in principle. So that's why we believe it's not, among other considerations, this is not the only reason, but that's an important reason why we believe this cannot be Higgs modes either in the single layer limit. A more promising candidate would be the existence of spin excitations, which are observed in many different unconventional superconductors. These are collective excitations intrinsically linked to the superconducting state. So they are whenever the material is superconducting, and they should disappear when the material is not superconductor, so when it becomes metallic. The usual shape that they show, it's something like more similar to what we see. It's a deep hump shape, as you see here, for these heavy fermion compounds, for this cuprate, and for these iron-based materials. And the energies also at which they show up are quite similar to those we observe below 2 delta. Okay, and actually there's a previous paper showing one universal relationship between this magnetic resonance that should appear in the density of states and the superconducting gap. So there should be a universal relationship between these two quantities. So if you look at the ratio between this the binding energy for this collective spin excitation in these many different materials. So here they collected many different spin excitations in many different in different families of unconventional superconductors, and then you plot this ratio. Basically, all of these materials lie or follow this universal relationship. So the energy, this ER, it's also it's omega. What would I show omega? So they follow this particular number. So we put the number or the ratio that we found in our experiment. It's basically exactly the same. It's 0.66. So it's quite close to the universal relationship that it's expected for unconventional superconductors. So this gives us first indication that this could be actually spin resonances. So in order to learn more about the origin of these spin resonances, we have studied both the temperature dependence of these bosonic modes and the magnetic field dependence of the bosonic modes. So here I show you one typical set, increasing the temperature from our base temperature at 400 millikelvin up to 1.4 Kelvin. You can see here at very low temperatures, we can distinguish 3 different bosonic modes: the fundamental mode, which is here, and some replicas here and here. So as you see, as we increase the temperature, still inside the critical temperature, these bosonic features decay. The amplitude of these bosonic features decay progressively and eventually die, actually within the critical temperature. So before the critical temperature occurs at 2 Kelvin, we see no trace of these modes. So I put these ideas into numbers here. Here you have how the critical temperature evolves. How the normalized, the gap behaves as a function of the ratio between the temperature and the critical temperature. It follows a BCS relationship. And this is the amplitude. In black, you see the normalized amplitude for this particular, the most visible mode, which is this one. And you see how it rapidly decays inside the critical temperature. So in order to rule out the possibility that these resonances are being faint or are weakened due to thermal broadening, here you have the expected evolution of this particular resonance if it was due to thermal broadening. So basically, what this fit is, or this curve is telling us, is that these resonances should be visible above the critical temperature if it was just due to thermal broadening. So there is something else that is killing these resonances. So the fact that they die with the critical, or they evolve, or they weaken with the as we approach the critical temperature, means that these modes are intrinsically related to the pairing interaction. And that's why they show up in the density of states. So we have also studied the magnetic field dependence, as you see here. Here's another set of that we have taken, the base temperature of 340 millikelvins. You see, in this case, both the fundamental mode at both sides clearly here in yellow, and some of the harmonics, both at empty states and occupied states. And as we crank up the magnetic field and we increase the magnetic field, the critical field, the second critical field of its material is around 2.2 Tesla, or well, depends a little bit on the size of the material, but it's around 2.2 Tesla. So well below the second critical field. You see here these resonances become weaker and weaker and weaker as we increase the magnetic field, and eventually also die within the mixed state. Right here, I show you how the fundamental mode is behaving with the magnetic field, and actually you can see, if you follow this fundamental mode, you can see that apart from becoming weaker and weaker and weaker, these resonances separate from the Fermi level as we increase the magnetic field in this way, in a nonlinear way. Okay, so this is for the set of the fundamental mode for the empty states, and this one is for the field states, and they behave in a similar way. So, but this is the energy with respect to the Fermi level. So if we now plot the energy with respect to the position of the coherence peak, which can be, you see, if we plot the evolution of the omega, so the binding energy of this bosonic mode against the superconducting gap for each curve, you'll see that these two quantities are surprisingly anticorrelated. There is a clear anticorrelation between the binding energy of the bosonic mode and the superconducting gap. This is clear anticorrelation, and this is something that I plot normalized by 2 delta, and all the values, or most of the values, lie below 1, and I explain you in a minute why. Okay, so this clear anticorrelation is something that has been observed in the past for spin excitations, or spin resonances, I'm sorry, in many different unconventional superconductors. Here I show you 4 of them using tunneling spectroscopy. You see that in all cases, basically the omega, the energy of this fundamental mode decreases as we increase the size of the superconducting gap. But in all these cases, this has been proven examining or studying local variations of the bosonic modes, not using the magnetic field, as I show you here. Here I show how this is anticorrelated using the magnetic fields. So in all these works, this relation has been proved, as I said, using local variations in homogeneities of the superconducting order parameter. And this is something that we also try to study in our system, and here is the result. Here you can see the evolution of the fundamental mode, the first harmonic and the third harmonic for all of the omega values, or all the superconducting gap values that we have. So we have used all the curves that we previously showed you for the histogram. So here's a bunch of them. And basically, all these correspond to the fundamental mode, first harmonic and second harmonic. And in general, all of them show a clear anticorrelation. Here I show you divided over 2 delta, and the only reason is because the previous papers also do it, because that's the signature of, so the signature of spin resonances is two-folded. First is this anticorrelation, and the second one is that the binding energy of these bosonic modes should be lower than 2 delta. So all these values in general should lie below 1. You see here, here, and here for this.
Miguel, you should be about to finish, okay?
Okay, so that's what we find for the fundamental mode as well. It's just below 1 electron volt in all the cases. So if we now plot the ratio between, or we plot the energy of this bosonic mode against the 2 delta, you see that all these unconventional superconductors lie in this particular line, and this is the case that for singular layer niobium diselenide. In order to rule out spurious effects from the substrate, because we have done all the experiment in bilayer graphene. So in order to to rule out the effect of the substrate, we have studied this having a single layer of HBN between the substrate and niobium diselenide. The electronic structure in the larger scale is quite similar. It's actually identical. The charge density wave is preserved in the system. If you look around the Fermi level, you see that the charge density wave, the superconductivity is preserved as well. And we also see these bosonic mode features. The only difference between this case and the previous one is that for some reason with graphene, we see a zero conductance in the superconducting gap. And it's not the case on BN. On iridium, we believe that iridium is somehow overlapping, or we are tunneling as well to the iridium substrate. Okay, so and with this, let me just wrap up my talk. We have been able to grow high quality crystals of single layers of niobium diselenide. We have studied I think we have demonstrated the existence of bosonic modes, which we believe are spin excitations in the quasi-particle density of a state. These are clearly intrinsic features of of niobium diselenide and intrinsically related to superconductivity. And the message to take home is that these bosonic modes, spin fluctuations, and in general magnetism should play a central role in superconductivity in niobium diselenide, and hopefully and likely in other two-dimensional TNG superconductors. Of course, this work leave a lot of new open questions. For example, the symmetries of the Cooper pairs, if we actually see a mixed singlet-triplet component as we expect in this 2D material. We also would like to, there should be more work, further work in order to understand the role of a spin fluctuation, each component, in the singlet component or in the triplet component, if it exists. And as well, we are also working on trying to understand the nature and the properties of the magnetic order present, either if it's magnetic or it's at the verge of being magnetic. So if I have a minute, I would like to give you some flavor about what is the further work that we are doing now. We are, since I remember, if you remember, I told you that conventional superconductivity should be highly sensitive to non-magnetic disorders. So what we are doing now is to study the superconducting state using alloys instead of pure niobium diselenide. We embedded non-magnetic single atomic impurities. Like in this case, for example, these are isolated atoms of molybdenum replacing niobium atoms, and we are studying the superconducting properties around these atoms. We are doing actual magnetic atoms, and basically want to go one step beyond the microscopy and the local characterization of these systems. And we are also working in trying to understand from the mesoscopic point of view these and other effects. So we're growing these materials on devices and trying to prove, to study the conductivity, magnetic resistance, etc., on these materials. And with this, I just finished. Thanking you all for your attention. Thank you so much.
Okay, thank you very much, Miguel, for this very didactic talk. So now time's open for questions. So now, in principle, you should be able to unmute your microphone. And Pablo here has one question. Please, Pablo, go ahead.
Okay, thank you. Can you hear me?
Yeah.
Yes.
Yeah, okay, great. So thanks, Miguel. I enjoyed the talk really very much. I wanted to ask you about the spin orbit coupling in niobium diselenide that you mentioned. In all these systems, it's rather important. Here, I believe it splits the shallow pocket quite a bit. And my question is whether this splitting, this spin orbit coupling, has any relevance in your mind to the spin resonances that you observe?
Well, I'm not sure if you mean that this splitting may
actually cause
take one of the subbands within the bi energy.
So actually, I believe the shallow pocket shows a very significant splitting due to spin orbit. So there is actually two shallow pockets apart from the deeper pocket. So that splitting has any consequence in the superconducting density of states? Could be related to your resonances or not?
Well, it's difficult to know. So there are two things regarding the spin orbit coupling. One is the fact that the Fermi surface is now spin polarized in one of in the K pocket, right? And that triggers, for example, the Eisen superconductivity in this material. And the second one is that this splitting approaches one of the subbands close to the Fermi level, and that may have an effect on the superconductivity. However, it's been estimated that the bi energy in this system must be around 10 milli-electron volts. So I don't think, in particular in niobium diselenide, this pocket or the onset of this pocket lies so close to the Fermi level. So in my opinion, I don't think the existence of this subband is affecting the emergence of these spin resonances.
Okay, so if I may, a follow-up question on this, is it conceivable that you could dope this system so that you polarize the shallow pocket, so you're between the two split subbands there, or is it really too much energy?
So in principle, it's possible, and that's one of the reasons why we are doing these devices that I just comment on. That would be a solid state gating, but that's medium-term project. Another way would be to chemically dope it using the suitable defect, and that's something that we are also doing. The problem is that if you add impurities in order to dope the Fermi, to modify the Fermi level, probably you are affecting superconductivity as well in several ways. So it's not clear what the effect could be in that regards.
Okay, thank you very much.
I can see how clearly it could be done.
Okay, we have another question from Herman. Herman, please.
Hi, thank you very much, Miguel, for this nice talk. So I wonder, could you please put again the transparency with the magnetic field dependence? Well, I think it was late. There it is. Great. There, for example. So I have here a couple of questions, if I may. So first of all, whenever you apply a magnetic field, there is a spatial dependence, and I really miss to know what happens as a function of the spatial dependence at zero field and magnetic fields. And then, so of course there are vortices, and the spectra should look like very differently inside and outside the vortex. And now the thing which really puzzles me is that with the 2 Tesla curve, you are, I mean, how is the density of states of the normal phase? You certainly know about the ideas of Altshuler-Aronoff and all these localization effects. So you could very easily make a sort of phenomenon of thinking like in universal conductance fluctuations, which gives you features in the density of states which are related to the superconductivity, but also to the normal phase. So how can you exclude this?
So Herman, well, you have a very sharp eye, and that's totally true. So we have done this series of these sets of measurements in different positions, trying to be in the superconducting region. It's been the initial plan was to image the vortices, but that's extremely difficult, or it has been extremely difficult for us. The only time we succeeded in doing this was something here in this image, where you can see the size of the typical size of the vortices, but it was fairly impossible. So we decided to try to do the same sets in different locations. That's one part of the explanation. The second part of the explanation is that it's true that when you, in general, go when you go above the critical field, in general, not always, but in general, what we observe, it's a V shape in the density states. In the normal state, we see a V shape. We don't know the origin of this dip. One of the options could be if it's a pseudo gap, or it's just a dip due to electron-electron interactions. So we don't know that. I have this slide to show that. This is the same region at 0 Tesla and 5 Tesla, well above the critical field, and we still see something. And that's what you saw in the upper curve in the set with evolution.
I mean, this is clearly an evidence to me that disorder, not a crystalline disorder, but electronic disorder, which is extremely interesting, is playing a significant role in your data.
So yeah, but perhaps we can talk later, because we are kind of puzzled about this. We have also measured tantalum diselenide, and we clearly see this feature as well. And it's not clear at all that it's superconducting anymore.
Thank you.
Okay, then Joaquin also has one question. Please go ahead, Joaquin.
Hi, Miguel. Thanks a lot for your talk, man. This is really very interesting. I also have a question about the magnetic field dependence. Very naively, I would expect that the energy of your excitation should go linearly, right? But it doesn't. So, what is your comment on that?
I don't have any clear answer to that. So this evolution is not linear. That's all basically we know. Right now, Paco is working with Fernando and Daniel, his student, in order to try to understand this kind of behavior. So all we know is that the fact that these features go away from the Fermi level indicates probably ferromagnetism. They are spin excitations, coming from ferromagnetism, ferromagnetism, but we don't know why they are not linear. We don't know why.
If you try to infer by the slope of energy versus magnetic field a magnetic moment, is this, of course, the slope is changing, right? But how does this compare with the Bohr magneton?
The slope here, you mean?
No, the other panel, the energy versus magnetic field. Yeah, if you choose the low field, well, so anyway, you could try to infer a magnetic moment there, yeah.
Okay. No, we haven't done it. But yeah, if you say so, actually, we will try to do it.
A final quick one, if I may. The magnetic field is always of plane, or?
It's out of plane. It's out of plane.
Okay. Can you do it otherwise, or that's a...
No, I wish, but I'm afraid not.
Okay, thanks a lot. Thanks a lot. Awesome stuff.
Okay, yeah, I think Isabel has a question but cannot raise her hand. So please, Isabel, go ahead.
Thank you. Nice talk, Miguel. I have a question because you have shown that this anti-correlation between the gap size and this energy of the bosonic mode, when you increase the magnetic field, and also when you look at the changes of the superconducting gap as a function of the position, but when you look at the temperature dependence, you see a positive correlation. So you see
the temperature dependence, you said?
You see a positive correlation. So you see that the superconducting gap is correlated.
Here, you mean?
Yes. So there, the size of the superconducting gap decreases, and the size of the amplitude of this, or at least is at the same position. It doesn't change the position of the
You're saying that it remains constant. The magnetic field, the size of the gap diminishes, so basically it becomes larger.
Yes. Well, I'm saying that the size of the bosonic mode, the energy of the bosonic mode, doesn't seem to increase when you decrease the size of the superconducting gap with temperature.
Yes, that is totally true, but I don't think that's against the idea of having a spin excitation. I cannot give you probably a good insight about it and why it remains constant with the temperature, but I don't see either how temperature could affect the binding energy of these bosonic modes. So I do understand that they become, let's say, mobile when you apply a magnetic field, because it's a result of a magnetic excitation, but temperature is, I don't understand why it should move. This peak should move with the temperature.
And what do you think is the origin of the spatial changes of the superconducting gap in your sample?
Well, they are quite small. They are quite small, actually. So we have had a hard time to plot this because, in general, it's quite homogeneous. In particular, using the samples that we use, etc. So most of the points lie here within less than 0.1 millielectron volt. The origin could be, I mean, the presence of edges. We try to do these things in far from edges, far from dirt clusters, etc., etc. But at the end, you cannot control atomic size impurities, or you cannot control the existence of grain boundaries. The size, I mean, the position of the edges, even if they are far from the place where you are measuring, probably will have an effect. We are talking about superconductivity, so the coherence lengths that we have to take into account are much larger. So probably all that yields to small modifications of the superconducting order parameter. But in any case, they are not large. They are quite small in general, I think.
Okay.
Okay, I'm not sure if there are more questions, because some people have unmuted their microphones but not raised their hands. So Lenny, do you want to make a question?
What I was going to sorry, do you hear me?
Yeah, Lenny.
Okay, so is that at some point I was going to ask whether at some impurities, not necessarily magnetic or non-magnetic, you have observed some kind of local state?
I will tell you in a couple of weeks, because this is a fresh result. We just were able to image these molybdenum atoms. We are playing with we're trying to decrease actually the number of molybdenum atoms to get them even more isolated. So we do observe the emergence of a flat band at minus around 0.5 millielectron volts, but far from the Fermi level. So we don't know exactly if there will be a clear effect on superconductivity, but I'll be happy to discuss this soon. Who is asking, by the way? Who is asking?
Lenny Vascones. Okay.
So Farhad also has one question. Please, Farhad. Farhad, I think you want to ask one question. No?
Yes.
Oh, okay.
Yes.
Go.
Okay. So, Miguel, thank you very much for this very good, interesting lecture. And I have the following question. The above gap resonances in conductance are well known long time ago. And usually they were related to the fact that electron hole pairs, Andreev type, for example, are confined or in superconductor or in some electrodes close to this superconductor. So actually, we also observe in our superconductors of 40 nanometer size above gap resonances. So how your resonances are specific for 1D superconductor and why it is not the same story as above gap resonances well known before?
So you're suggesting that these resonances may come from the fact that the system is confined?
Yeah, these resonances, for example, when the electron hole pairs are confined in superconductor, they have named Thomas resonances. And I don't remember exactly when they are confined in the electrode close to superconductor, they have another name, but they were well known. We observe experimentally the same resonances in 40 nanometer thick vanadium superconductors when there is an electrode like iron, which is confined with two barriers. So, and our resonances have also many periods, etc., etc. So, you can see the pictures of these resonances in our paper published this year in Physical Review Applied, figure number 5. So my question is, how specific and what is the new physics behind the just geometric confinement of electron hole pairs in your system? What is the specifically different? That I don't understand.
Yeah, that's something that we considered in the past, that the possibility that they could be features coming from the confinement. But if you make the numbers for the system, the coherence length of the system is about 100 nanometers, which is not small at all. But basically, we are using samples like the one you see here. This is a good sample where the neighboring diselenite is continuous. So of course, these steps that you see here are coming from the silicon carbide, but the system is continuous. So in principle, there are no boundaries confining the material. It's true that we have also done part of this experiment on samples with lower coverage, and that leads to measurements in, for example, let me show you. Regions like, for example, like this, which is like half a micron size. But yet these regions are 5 times the coherence length of the material. So we don't think we are close to the confinement. In any case, we try to avoid measurements on small regions like this and like that for that reason. And in general, regardless of what you measure, in general, you see the same features of the same energy. So I don't think confinement is an issue here. That's all I can tell you about it.
Mm-hmm. And if you moved above TC, there was a black data, black points, where the extrapolation, so there were red points and black points, amplitude as a function of temperature, where for black, you extrapolated that the resonances persist above TC, and for red, they were just disappeared. So what is the meaning of this?
No. The red points basically is the gap size.
Yes.
Normalized to the gap at 0 Kelvin, and the black points is the amplitude. The amplitude of this particular one. Just wanted to show you that it decays faster than the thermal broadening.
Okay, thank you.
Okay, so we have one more question for Somes. Please, Somes.
Hi, can you hear me?
Yeah.
Yeah, thank you for a very nice talk. I had a question regarding your the energies of the field and empty resonances. Why they are different in energy? Why they are not symmetric?
Where?
So when you
the
field and empty state energies, the energies for the resonances. Yeah.
So you're talking about, for example, this curve where we don't see.
I think in the next
one?
slide. I think in the next slide, somewhere later, where you put the field and empty resonant energies, I guess.
So in any case, I think I can respond. Why the amplitude is not symmetric?
The energies are not symmetric. I think the energies are different also. The energies for the positive and negative.
Well, they could be. They are not exactly the same, but I think it's within 100 microvolts. Probably it's about the same. I don't know. So it's true that sometimes we see one harmonic or the fundamental mode and the other one are not exactly at the same energy, but the differences are, well below, let's say, 100 microvolts.
Okay, thank you.
Okay, so if there is no other question, I think we had already plenty of them. So we thank Miguel Moreno for his very nice talk. And I would like to tell you that next Thursday, we will have Felix Zamora, who will give us a talk also in this seminar series. And I think he will be talking about antimony related things. Okay, thank you all very much. Thank you, Miguel.